The linked list, although often overlooked, is a fundamental data structure in computer science. In Chapter 1, we're going to focus on the singly linked list, and in Chapter 2, we're going to cover the doubly linked list. Before we dive in, please subscribe to our channel and enable notifications to stay current with our latest content. Your support helps us create more informative and valuable videos. In any case, let's start with Chapter 1, where we're going to examine the workings of a singly linked list, but for simplicity's sake, we'll refer to it as a linked list throughout this video. A linked list is comprised of nodes. Each node holds a value and a link to the next node. If you really want to understand the underlying mechanics of a linked list, we need to unveil the curtain and look at how things are actually being stored in memory. Think about memory as a sequence of storage containers, where each container is called a byte. A byte can hold up to 8 bits of data, with each bit representing a binary number, either 0 or 1. Each byte is stored at a unique location, a unique memory address, similar to how your home address identifies where you live. This piece of data lives at the memory address 100B. If I want to store a value like 56 at a memory location like 100D, I can convert the number into binary by repeatedly dividing it by 2 until I can no longer do so, and then recording all of the remainders. However, for large integers such as 700, the division process generates 10 remainders, which cannot fit in an 8-bit byte. So we reserve 4 bytes in memory from the starting address. 4 bytes can hold 32 bits, which is more than enough to store the binary representation of 700. Now, to avoid the hassle of determining the storage needed for each value, we're going to keep reserving 4 bytes of storage for every value in this video, and rather than representing the data in binary, we're going to stick to their original format to save some space. Sound good? Cool. With that out of the way, we can dive into the main topic of this video, linked lists. So, how do the nodes of a linked list, such as the one you're looking at right now, actually store in memory? The first step is to reserve a contiguous block of memory for each node. The term contiguous means that the memory locations are physically connected without any gaps or interruptions. A simple node contains a 4-byte integer value and a reference to another node. So the runtime allocates a contiguous block of 8 bytes in memory. The first 4 bytes holds the value, and the next 4 bytes keeps a reference to the next node. The reference starts off as null because there's no other node. Now let's say we want to add a second node to the list. Once again, we allocate an 8-byte block of memory for the node's value and reference. And how do we link these nodes together? It's pretty simple. We update the reference of the first node to point to the memory address of the second node. The first node of a linked list is called the head. It's going to be the entry point because it's the only reference that the programmer can access. And so to add a new node, we start from the head from the first node, which contains a reference to another node. So we follow the reference. And because the second node contains a null reference, we know that it's the last node. So at that point, we can store the new node in memory and reference it from the previous node. So now we've got a linked list of 3 nodes. What if I want to add another node? Once again, we start from the head and we traverse the nodes one by one, following their references until we find a node with a null reference, signaling that it is the last node. Only then can we store the new node in memory and link it to the previous node. As you can see, adding new nodes to the end of a linked list can become increasingly inefficient as the list grows larger and larger. It follows that the linked list is very weak at adding data from its tail. Alright, now we can look at removal. This operation intends on removing the fourth node, so we'll have to imagine 5 blocks of memory. To find the node we want to remove, we start at the head and move through the nodes one by one, following their references. Once we find the node that we want to remove, we can disconnect it, update the reference of the previous node to point directly to the next node, effectively bypassing the node we want to remove, and then over time the system will reclaim the memory occupied by the disconnected node, essentially removing it. So as you can see, the inefficiency in removing a node from a linked list lies in the process of starting from the first node, the head, traversing through each node until we find our target, and only then updating the reference to bypass the node we want to remove. Removals from a linked list are not efficient. Now, retrieving data from a linked list is also inefficient. This operation wants to retrieve the value inside of node number 5. Similar to the removal process, when searching for data in a linked list, we must start at the head and traverse through each node one by one, following their references. As we travel from one node to another, we keep count. As soon as we count 5, we know that we've reached our node and we can return the value inside of it. And so, retrieving data is also not efficient. Think about it. Unlike other data structures like arrays, we don't have direct access to a specific index in the linked list. We need to follow the references from one node to another, keeping count of every single step that we take until we reach the desired node. Not good. Okay, we've discussed the weaknesses of a linked list. We should also highlight some of its strengths. The key advantage of a singly linked list is the speed at which we can insert or remove data from the beginning. So if I want to insert a new node at the beginning of a linked list, we simply allocate memory for the new node, store its value and reference, update its reference to point to the current head, and then we update the head to point to the new node. This process is really fast because we don't need to traverse the entire list. Similarly, when it comes to removing data from the start of the list, the process is efficient. First, we update the head to point to the second node in the list, effectively disconnecting the first node, and then the system can reclaim its memory. The great thing about adding or removing nodes at the beginning of a linked list is how quickly we can get it done. We don't have to go through a whole chain of nodes. Alright, now we can move on to Chapter 2 and discuss the doubly linked list. A doubly linked list, as the name suggests, consists of nodes that have two references, one pointing to the previous node and another pointing to the next node. A doubly linked list is very effective at inserting data from either end, removing data from either end, and is not weak but moderate at retrieving data. Let's see this in action. How do the nodes of a doubly linked list, such as the one you're looking at right now, actually store in memory? Like before, we need to reserve a contiguous block of memory for each node, and in memory, each node will occupy 12 bytes, 4 for the value, 4 bytes for the previous node's as reference, and 4 bytes for the next node's as reference. Both references start off as null because there's no other node before or after, and the first node is called the head. And as you know, the programmer has direct access to the head, they can use it to enter the list. Now let's say you want to add a second node to the list. First we allocate a 12-byte block of memory for the new node to store its value and the two references. We then update the second node's previous reference to point to the head, and the heads is next referenced to point to the second node. This connection ensures that the nodes are properly linked. The second node, which happens to be the last one, is called the tail. The programmer has direct access to both the head and the tail, which means you can perform operations from either end of the list. If you want to add another node at the end, we allocate another 12-byte block of memory for the new node, and then we can update the nodes as reference to point to the current tail, and the current tail itself will point to the previous node. The fact that we can add data from the head or from the tail is what makes doubly linked lists so strong at inserting data. And without even delving into the memory level, we can already deduce that removing data from either end of a doubly linked list will be efficient. If the node we want to remove is close to the head, we can start from there and take the shortest path to remove the node. If the node we want to remove is close to the tail, we can start from there and take the shortest path to remove the node. If the node we want to remove happens to be at the head or the tail, then it happens right away. As for retrieving data, a doubly linked list will generally be faster than a singly linked list. If I want to access the node with a value of 1, I can start from the head and take the shortest path. If I want to access the node with a value of 4, once again I can choose the starting point closest to it and take the shortest path. I would say that the doubly linked list is moderate at retrieving data. I would not necessarily say that it's strong. The reason is that in the array data structure, no matter where the element is, you can quickly calculate the memory address, whereas with doubly linked lists, you still have to go through the process of going from one node to another. So in comparison to arrays, they are not fast, but they are still relatively better than the singly linked list. And when all is said and done, the doubly linked list is a much more versatile data structure than the singly linked list. So why would you ever bother using a singly linked list? Well, keep in mind that each node in a doubly linked list contains 2 references and therefore requires more memory. So while it is more efficient than a singly linked list in almost every task, it does consume more memory, so that's something you should keep in consideration. In the next video, we're going to look at hash tables, which combines arrays and linked lists, and it is a very powerful data structure. I hope you're excited, and if you enjoyed this video, please consider subscribing to this channel to stay updated on more videos that we're going to release. Thank you for tuning in.